Before we dive into this, I want to kind of understand what kind of audience we have. How many of you have done digital engineering or MBSE type work before? Oh, great. We can make it up together. I love it. There's only like one person. So that's
we'll
awesome.
direct all the questions over there.
We'll direct the questions over there. No, seriously though. So we're also kind of new to digital twins, digital engineering, and so we've gotten some funding. We'll talk a little bit about that, and we're starting down this path to try and figure it out, and the role that test and measurement plays in it. So this presentation is kind of more of a what Testeract is working on, and kind of our vision and the roadmap that we're taking to integrate test and measurement with digital twins. And so feel free to ask any questions at any point, yell them out. If you need a microphone, we can probably grab one and run it to you. We got a runner in the back. He looks really fast too. So feel free to ask any questions. But most importantly, if you guys want a t-shirt, go to our booth and we've got some free t-shirts. I mean, they weren't free for us, but they're free for you. So
we don't want to check the bags and bring them home.
Tell them that I sent you, and so you can get one. We don't want to take any of the shirts home with us. It was excess baggage, and so I'm Sam Roundy. I've been doing automated tests for about 20 years. I have a CLA, CTA, a LabVIEW champion. How many people use LabVIEW in here? Oh, good. We can talk the same language. How many of you use Teststand? Okay, that's about the ratio I would expect. I actually grew up on a farm in southern Utah. We had about 200, 300 acres of alfalfa hay. We had some cattle, sheep, and different things. So that's a little bit about me.
So my name is Garrett. I'm the VP of R&D and Products at Testeract. I'm also a co-founder of Testeract. Sam and I founded the company together in 2015, so we have a long history. Sam's still crazy enough to keep going with me.
I tried to quit the other day. He wouldn't let me.
Yeah. But I also have 20-something years of experience in the automated test industry. I've done everything from downhole telemetry networks to radio astronomy, so everything from heaven to hell. And I also grew up on a farm, which is what makes me qualified to talk today.
So at Testeract, we have about 40 engineers. We specialize in automated test software stack, all the way from talking to the devices to putting your data into your data storage and analyzing it. We also build hardware, but we're more focused on the software side. So cool, let's get going. We're gonna talk about our vision. We're gonna talk about our view of automated testing, and then kind of how we see digital twins and digital engineering playing a role in that, and then kind of where we're going a little bit. So automated test engineering is pretty straightforward. You have some kind of execution engine, whether you build that yourself or you use Teststand or some kind of test executive. The engine runs through some test cases or some scripts, and it talks to your instrumentation. That instrumentation is either stimulating your device under test or your unit under test, and measuring things off of that device under test. And then that data is getting collected, analyzed, and stored, and presented in a report or a data sheet or some kind of format that you can consume and know how the unit under test performed, right? So this is a very kind of simple view of what that test software looks like and how it interacts with the UUT. The reason that we're kind of highlighting this, I think all of us have done test and measurement, but we want to kind of establish a framework or a baseline for some of the slides that we're going to talk about today. And so that's why we want to present it like this, especially those test cases and those libraries up there. When you look at the role or kind of the product life cycle, test is done at like a lot of different phases. You have environmental testing. You have at the design side, you have your V&V or your design verification stuff. Over on the production side, you have like full automation. You kind of have some low rate production, different things. And at each of these phases, you have to build test systems. And just quick show of hands, how many of you have to build a completely different set of code and test system over in your production side than they do in the design side? Oh, that's surprising, only a couple. Everywhere I've seen or worked at, it's like usually on the R&D side, they build it and then they throw the product over the wall, and then the operations guys or whoever's on the production side has to go rebuild a test station to test this unit under test. And these test stations, they take a lot of time to build, both the software and the hardware. And, sometimes a couple years or 3 years, depending on how complex they are, especially if you get like the big 4-6 bay rack stuff going. And we have a framework. We'll talk a little bit more about that, but we've been able to shorten some of those build times. But the goal of this whole presentation is really to identify how we can get these as short as possible, these development times, especially around the software. So kind of watch for that as we go through this. So now we're going to kind of establish what digital engineering is, at least set a baseline for the group here today. What we're finding out is that digital engineering means something completely different to everybody in the industry. You go talk to BAE Systems, it means this thing. You go talk to L3 Harris, it means this thing. You go talk to Raytheon, it means something else. You go talk to ANSYS, they have their own idea of what it should be. And so it's all over the board right now. The Army, they have a group that's trying to set the standards for what digital engineering is, especially around SysML. How many of you used Cameo? Okay, perfect. So I can make up what it really is. No, just kidding. Cameo is kind of a tool that's used a lot in digital engineering to define, it kind of defines what these SysML things are. The SysML is like a markup language that defines what your digital twin is. And so a digital twin is supposed to be a virtual representation of your actual device under test or your unit under test, your module, whatever it is that you're trying to build. And that's made up of a lot of components. You have your behavioral, definitions, your requirements, your structure, your SPICE models, your MATLAB stuff, whatever it is that makes up that unit under test. And our argument is that, and we're in alignment. I don't know if you guys know Greg Brown and I. We've been kind of working with him on some of this stuff, but our argument is that your test results or your test plans, those test cases, they need to be a part of that model as well, so they can be a part of the feedback system. And the whole goal is that this digital twin represents what you're really going to build, and that when you really build it, you can feed information back into this digital twin to make the product better in the future, right? So that you can iterate a lot faster, so you can have a better product and all of that. Yeah, this is a definition I pulled off the web of what digital engineering is, so you can read that. It's probably more accurate than what I just described. Any questions so far? Because I still have a ton, so. Okay, so the goal, again, your virtual device minus some of the requirements and analysis stuff should equal your physical device when you actually go print it. The idea being that you don't have to make as many physical devices. You don't have to iterate as much in the physical world. You can iterate a lot faster in the digital world and get to production a lot faster. And so why is there such a push for this? I think you guys have kind of picked this up either at this conference or other things that you've read or seen online, but there's a lot of stuff coming down from Congress, from the DoD, from the industry, automotive especially is pushing a lot of this, and it's coming down and it's saying, hey, we need to just get to market faster. We need the war fighter stuff faster, and so that's why this push for model-based system engineering as well. It should be able to reduce costs. I don't know if they're seeing that or not. The stuff I've read, it's kind of sketchy of whether it really is reducing cost right now. But in the future, it should reduce cost because you don't have to iterate as much on the physical side. And then this is another slide from specifically from Greg Brown. The purpose of this slide is to say you have your models of your UUT, but you also need to consider these additional models, which are your requirements, your test capabilities, your test assets, digital twins of your instrumentation, things like that. And together, all of that adds all of this value around digital engineering, because without this piece, it's just a model and you're not getting a lot of this value that you could otherwise get out of your models if you didn't add those as models as well. And so we're going to talk about specifically how we can get some value out of having your test cases, your test capabilities as part of that model.
Yeah, thanks, Sam. So getting a little bit more towards where Testeract actually got really interested in this problem and why it piqued our attention. As we began to think about what testing means, not only in the physical world, which we've been working in for a long time, but in the virtual world, in the digital world, we started to consider what this would mean in a test framework. How would we interact with that digital twin? So if you look, you'll see that as we imagine our test scenario, replacing the UUT, the physical UUT, is a digital UUT, a digital twin of the UUT. And as we imagine interacting with that, the input signals and the output signals, how would we talk to that functional model of the UUT? We started to ask ourselves a lot of questions. A little bit of background before we get to some of what we think is the answer. Testeract has a framework that we've been working with for a long time. The main components of that framework, I'm not going to get into super detail, but the main components are the hardware abstraction layer, which you'll see in one column there next to the test bench. The central component of that is essentially the test executive and the data acquisition component of it. And the component on the right is the user interface. So we've been using this framework for a long period of time to a lot of success in the physical world. We started to ask ourselves, how can we apply this to the virtual world?
It's also important to note that the framework is, we never make monolithic builds at Testeract. It's always Lego pieces that make up your test system. And so it's a bunch of consumable binaries that when you put all of this software together, it works. So our build times are never more than like 30 seconds or a minute, because it's all these little Lego pieces that we just consume in and they all connect together and work. And so that's why that's a crucial piece of information, because when we talk about the how, it's important to understand that those Lego pieces can just be interchanged like that.
Yep. So applying our framework to the problem, as we highlighted it earlier at a high level, we started to imagine how would we talk to, well, first of all, the physical unit under test. This is what we do in practice. We take our test executive gets those test scripts. Those test scripts are fed in from as part of the definition of the test, and that's part of the central piece of the test executive. But our hardware abstraction layer plugs in, and that's how we talk to the instruments on both sides, both on the input and on the output. And that's how we interface with the unit under test. It gives us a lot of power, the ability to swap out and talk to different models of instrumentation. It gives us the power of session management, being able to handle those sessions with the hardware and share it across multiple GUIs or automation through test stand. We do that all the time. And so we would apply that to the virtual world. How would we interact with the virtual world? And we started to ask ourselves, what would a how look like when it talks to the digital twin? We need a script, to be able to talk to those models. And we started to say, well, why can't we do this with our how as well? Why can't we take the test scripts in the same manner in the virtual world and do that as well? So for a long time, we've been using simulation classes in our hardware abstraction layer. For a long time, we've seen the value in creating simulations so that we could develop our automated tests before the customer or a vendor shipped hardware to us. We'd very, very often have really tight deadlines for our projects, We had to be able to develop automation outside of being able to have the entire rack built for us in the lab already. That had to happen in parallel just for us to meet schedule demands. That's very often the case for those of you that work with large labs. You might have environmental stress tests where you have temp chambers, and I've very often seen the case where there's almost fights over who gets the temp chamber next, who can get to the resources next. So we've decided to parallelize this a long time ago, and we've developed a lot of simulation a long time ago. As we saw the value in that, we started to realize as we became more introduced to the digital engineering problem that we could reuse some of those same ideas of simulation here, because our HAL is a very plug-in based architecture. It's using dynamic dispatch in LabVIEW or polymorphism outside of LabVIEW to be able to call different classes during runtime based on just a configuration file change. So we can imagine several different workflows, the first of which you see up here, which is that we're directly interacting with the model by setting the values of pins on the inputs and the outputs to talk to the UUT or the digital twin of the UUT. And by doing that, we're able to interact with the UUT and get value out of that workflow by essentially testing it in a completely digital environment. Second possible workflow, and one that we want to work on. We haven't done much development in it yet, but we've started to work with Greg Brown and others from NI, and others actually outside of there, is being able to work with the digital twins, so a simulated functionality as well as requirements for test instrumentation itself, and have those digital twins interact with the digital twin of the UUT. This is another possible workflow that we can imagine just using a configuration change in our hardware abstraction layer and a separate model plugin class for our hardware abstraction layer. And we will be able to work through that workflow as well and get a lot of additional value out of it. So not only is it now just interacting directly with the UUT, but you start to get a notion of what does the entire interaction of my test system look like. That's a really important one for us. And we'll talk a little bit more about the value of it later. Go ahead.
If you're going to talk more about it, then I won't.
No, you're good. So finally, we get to the physical world. This is the third workflow. Again, it's just a configuration change. Now we're going through the physical model classes, where in this example, we had a Keysight 6700 and an iDAC-MX, analog input, maybe card on the other side. But we're talking to the physical UUT. This is the same automation code, so my application level code doesn't change. All that changes is a configuration setting, and I'm now going from the virtual world over to my real test system. The power in being able to switch between those two without having to change my application level code is enormous for those of you that are in highly regulated environments. When you have a monolithic build and you go to change your application in one tiny place, and then your regression testing takes a month because you have to prove that out to your quality team. That's a nightmare. But when I have modularized my architecture, and now I can prove that I only changed this one tiny piece, and now my regression testing only takes a couple of hours, that adds an enormous value to your process. So that's what we're driving towards.
The other advantage of using the same test scripts on your digital twins that you can in the physical world is, first, you don't have to recreate them. So that's a big thing. And the other thing is you're performing the same exact tests on both the virtual and the physical, and then you can compare those and see how closely it was built to what your digital twin was.
Yeah, thank you, Sam. So in the digital engineering world, they will call that model calibration. So you're actually refining your models, and we'll talk about that more a little bit later as well. So I've alluded to this already quite a bit, but in the end, we can imagine a test development process which is dramatically changed. First of all, if the models include our test cases as part of the definition of what the model of a DUT is, then I can actually take those models, if they're well structured, and we're working with standards bodies to begin to be part of that conversation around what that structure really looks like, then we can auto-generate test code from the models. And that's not far-fetched. That's actually been prototyped. So The test scripts can be executed by the test point engine. At its heart, test point currently, which is our framework, currently uses Testan as its test executive. So you can imagine executing those tests and both the digital world and the physical world. Test point. So the plugins for the UUT and the digital twins of the instrument and the physical world as well can also be created and largely reused if they've already been created. So you have these reusable libraries. You begin to create this digital asset library, which are virtual or digital twins of your instrumentation, and you can reuse those pieces over and over again, just like we currently use the reusable pieces of our hardware abstraction layer today for our framework. Another advantage of this new imagining of the process is that the digital workflows get tested and fully validated. For those of you that are working in digital engineering, you understand the value of the digital thread and the fact that when you change one model in a set of interacting models, you can see how those changes instantly propagate to everything else, how they impact your pass-fail criteria, or whether or not things will pass or fail before you physically build the thing. We'll have high confidence. This is another very often overlooked but very important component of this, is that you'll have high confidence in your physical test system design, and that you can test not only the UUT in the virtual world, but you can test the entire test system. And you'll have confidence that when you go do acquisition, when you tell people to go buy these components to build out a test system that have very long lead times and very high costs, that they can have confidence that you bought the right thing for the job. And then we mentioned this a little bit earlier, but no changes in the algorithm, in the application level. It's really only configuration changes. And then you get that reusable digital asset, and you start to build a library of those. So you can reuse those over and over again for new test system designs. Finally, and Sam showed earlier, we're currently driving down test times or test development times to about 50% of what we see on average out there in the market. We want to ultimately use what we're doing here to push much of the iteration and development for test systems far to the left side of the curve, and ultimately drive down development times for test systems dramatically by another order of magnitude. That's where we're headed with all of this.
So yeah, I mean, to Gary's point, the digital threads and where that plays into it is, once we have that physical device, that unit under test, and we start testing it, we need to take that data and feed it back into those models so that later on in the iteration of that product, as you do bug fixes or maintenance fixes, this data can quickly tell you, hey, you need to fix this component over here, or this thing's bad on your thing, and that will help you respin your DUT or your UT a lot quicker. So that's kind of the idea of this, is that the data, because you're using the same test cases that you used on your digital twin, and that data that you collect from your physical device, you can feed that back into your models and make better improvements, smarter improvements, right? So, any questions so far? Do we have one? All right, here.
Digital twin.
You say again?
How did you develop the digital? What software did you use to develop the digital twin?
Okay, so the question is, what software did we use for the digital twin? So we kind of said this at the beginning. We're in the early stages of doing this.
Okay.
Most of the time, the software for digital twins for the DUT or the UUT, it goes back and forth, The software is usually done in like Cameo is kind of a very popular one with the SysML stuff. And then the actual, I guess, behavioral models are done in anything from some kind of PSpice or something, all the way through to MATLAB to other things as well. So it's all over the board. And that's part of the problem right now that we're finding in the digital twin world, digital engineering world, is that there are no standards. Okay. And so everybody just kind of makes up their own standards, right? So Sometimes the digital twins are just Excel spreadsheets, which is like, okay, I guess that works for you.
Yeah, you kind of have to separate conceptually the definition piece, which is going to be SysML, and that's made, you can make Cameo System Modeler or other things, from the functional piece, which is just seems to be all over the place. A lot of custom coding, other things.
Yeah. One concern or question that I have is, let's say the EUT, right? You call EUT, DUT. Let's say it takes an input of on or off, Boolean input or a fixed DC voltage, and then you know what you expect at the output. You can easily model that, right? But let's say, for example, your DUT is expecting 10 kilohertz waveform or 1 megahertz waveform, right? Now, when you use the hull to switch the API to model direct, right? Now we are limited to the speed of the PC, right? You are not going to be able to call the model at 10 kilohertz speed or 1 megahertz or 1 gig, whatever the speed, right? So now we are getting into high speed. Now we are not in Windows anymore. We are going to real time or FPGA, right? So it makes it complex, right? When you are talking about a simple UT, yes, this model is good. And it's relative terms. In effort is like, yes, from 6 months, I can go down to 1 month, 5 months savings, right? But if a digital tune, the digital twin itself requires 6 months of development by having all these complex environments, then wouldn't it make more sense to just use the EUT directly?
Maybe if you have the hardware already. The other thing that you should consider, I think, and this is just my opinion, is like Sam mentioned, we're new into this, is that just because your waveform may be varying at 1 gigahertz sample rate doesn't mean that you need to execute the model at that speed, right? You can slow down what's happening in the sampling and the calculations, and then sort of speed it back up as you get your data, your results back together at the end and see what the results were. So I think you don't, well, can't say for every problem it's good to go back and do the digital twins. There's a very specific example that we talked to some engineers at Lockheed about a couple of weeks ago. We were at another conference, and they said, we work on the F-16. We're going to keep selling F-16s for a very long time because we sell them to some of our allies, but we're not going to go back and make digital twins of every subsystem in the F-16 because it's not worth it to us to do so. Now, for the F-35, well, for the new components coming out, they're definitely going to have digital twins, but it's just not worth it to go back and do that for the old stuff. So those value judgments, they definitely have to be made. I don't think this is a categorical solution to every problem, for sure.
Okay, thank you.
Any other questions so far? How are we doing on time?
I don't know. We have a
2:30?
timekeeper.
Oh, we're going to get done way early then.
Yeah, we're good.
That'll be awesome. We'll give you some time. So Testeract, like I said, has gotten some funding through a SIBR, and we're in the early stages. We're looking for partnerships. If anyone's interested in talking to us about this, let us know. But we're working with the Air Force right now, and we're their standards committee and different people like that. So I think this is coming. We see it everywhere. A lot of our customers are starting to do it more and more, and they're asking about it more and more, which is why we started investigating it. And so I think it's going to hit. We'll see. There's a lot of skepticism around digital engineering. Some of that skepticism is it really worth it? Is there ROI there? And we got to figure that out, right, as a community, to see if there really is. So it'll be an interesting journey.
We've seen similar skepticism as we built out our framework in a lot of ways. We currently support around 1,500 different models of hardware in our house, sort of out of the box. But it took a long time to get there, and we keep adding to it as we go on in time. We keep adding more and more support for more and more instrumentation. So I can imagine a scenario where as we go on and build out this digital asset library, you sort of reach critical mass at some point where the majority of the things that you want to simulate in the virtual world have now been created for you ahead of time. So you don't have to pay so much for creating those digital twins every time you go to create or to interact with them in the virtual world anymore. But we're not there yet.
Last but not least, we want to do a shout out to Greg Brown. We've mentioned his name a few times. He's been helping us a lot. He presented with us a few weeks ago at a modeling and simulation show, but some of the slides he helped put together. So just a shout out to him. So
Yeah, he's given us a lot of feedback.
any questions? Yeah, I got a couple up here. We got a microphone coming right here. Then we'll get to you.
You mentioned that if you have a model of the UUT and the test equipment, you can potentially generate test cases or test scripts, and that you've even potentially prototyped something like that.
Yeah.
What tools are involved in that? Is that still a Cameo
So
capability?
there's some assumptions and some glue pieces that had to be made to make that happen. Greg actually has more details on that than I do, but I can give you a high level of what they did. There's another standard called ATML. It's not SysML. It's not adopted into that world yet, but there's discussion going on about whether or not they can adopt IEEE standard 1641, which is signals, and 1671, which is definitions around how you would define a UUT, not just including the functional piece, but references to all of the other pieces of information you would need to know, like inputs and outputs, other documentation, test requirements, things like that, test plans. So pulling in those other standards and then writing code to map the SysML to that standard, there are tools that will then take ATML and auto-generate test stand code from ATML. NI has that tool today. So using that kind of obscure little corner of test stand, you can auto-generate test stand scripts from it. Now, how broadly reusable is that? I don't know. It was just one prototype, but that has been done today. But it just required pulling in some extra standards, and there's some discussion around trying to get those standards to be adopted specifically as a subset of like SysML 2.2, but for test equipment. There's other things that we would like to be part of the conversation for, which are, for example, if I was to define a power supply, I have a set of methods that you can imagine for a power supply, which are like set voltage, turn on the output, turn off the output, and so on. Defining those interfaces is actually really important to the reusability of your hardware abstraction layer. So we want to be part of that conversation too. It's like, let us help you define the interfaces, because we've already gone through the blood and sweat of figuring out this the hard way. So let's reuse what we've done too. Yeah,
and I don't think they were auto-generating the test cases. I think those were manually created, but then they were manually created as part of the model, but then they could take that and auto-generate the actual code.
Yeah. That's interesting. Thanks.
Yeah.
So for your digital twins, how do you handle physical buttons and things that users interact with? Do you simulate that? Do you have a front panel that you would just alter buttons on directly? And then do you also go so far as to handle faults with those devices?
That's probably beyond where we are, honestly.
Yeah, I haven't encountered that case, to be honest with you. So I haven't contemplated it too deeply, but
I mean, at the end of the day, your button is going to be an input to your model, right? Mm-hmm. And so you're going to probably have, and I'm totally speculating here, is that you're probably going to have a SysML pin that says you're pushing a button that's going to trigger a relay or something inside of there on your model, and then that will tell the rest of the model to do whatever it would do when that button's pushed, right?
Okay, so you'd bypass the physical aspect of pushing a button and then just represent the result.
In our automations today, whenever we have to tell the user to do something like push a button or something when we're testing something on the physical world, we usually have a pop-up that tells them to do that. Well, we could make a HAL around that, treat the human as a hardware, as an instrument almost, and then go set that pin digitally through that hardware abstraction layer.
Yeah, we do that with our HAL currently. Sometimes it's like, hey, go pick up the DMM, take a measurement on these 2 points on the board, and then type in the value that you read, because there's no automation to get that to happen yet for that system. So we can imagine doing that as well.
Thank you.
Any other questions? All right, well, thank you for attending. Hopefully there's something useful out of this. We appreciate it. Have a great rest of the conference.
Thanks, everybody.